Hi, this is Olivia and Kyle, and we're here to present our heat exchanger design for Project 2. Background information for this project included designing a shell and tube heat exchanger to cool a computing center using a local water reservoir. The heat exchanger should be easy to clean and fit within a reasonable space. The design must also meet specifications outlined in ASME's boiler and pressure vessel code. It also must be able to accommodate a specified thermal load created by MSU's computer center. MSU provided many design parameters that we had to consider while designing our heat exchanger. The first was that 1 megawatt of thermal energy needs to be dissipated constantly. Also, 1 million gallons of water per day can be used for cooling with a uniform flow rate. The temperature of this water is not to rise past 60 degrees Fahrenheit. It is initially at 57 degrees. The current pipe inner diameter is 14 inches, and the heat exchanger should not be any longer than 25 feet. The hot flow starts at 120 degrees Fahrenheit. We decided to use propylene glycol for our hot flow fluid because of its heat transfer properties. Also, pressure drops are to be minimized in our heat exchanger. During the design process, we tested several iterations of heat exchangers. We modified structure material, hot fluid mixture, baffle spacing, tube length, and the structure geometry. The limiting factor is the cooling water's ability to dissipate heat. We would need water that has a higher flow rate, or we would need more flexible temperature constraints in order to dissipate a full megawatt of heat. Without the changing of these constraints, it's pretty much impossible to dissipate the full goal of a whole megawatt. Because of this problem, we've chosen to focus the optimization of our design for cost and size of the heat exchanger and not worry so much about the megawatt of heat needed to be dissipated. The heat exchanger geometry is a critical aspect of optimizing the heat exchanger. Shell and tube heat exchangers are mostly divided up into three main parts: the front head, the shell, and the rear head. For our configuration, we chose to go with a BEM structure because it is very easy to clean and is low cost. Next thing we needed to optimize was the tube pattern. We chose a 45 rotated square arrangement because it is also easy to clean and is a very efficient process. We also wanted to use aluminum because it is a cheap material but will still be good enough for our heat exchanger, so we'll save a lot on cost. The last thing we needed to optimize were the tube length and baffle spacing. We chose a tube length of 8 feet with baffle spacing of 6 inches to comply with the standards for heat exchangers and to make our heat exchanger very efficient.
Here's a blueprint design of our heat exchanger. You can see that the total length of the structure is 126 inches, and that's about 10.6 feet, which is much lower than the 25 feet requirement that we have available to us. During the heat exchanger process, we had to go to the process tab and put in design variables for the cold side fluid and the hot side fluid. We knew variables such as the inlet and outlet temperatures of the cold side as well as the mass flow rate, and the hot side we knew the inlet temperature as well. Unknown variables were optimized to produce the highest efficiency and heat dispersed as well as the smallest pressure drops. You can see from our results page that our heat exchanger was able to dissipate 0.333 megawatts of heat. That's 1/3 of the 1 megawatt that we had set out to achieve. However, this was mainly due to the limiting factor of the cold water feed. As we said before, the heat exchanger could dissipate more heat if there was a higher mass flow rate of water or if there were more lenient temperature constraints involved with the water temperature. In designing this heat exchanger, the total cost would be $42,855. The cost to build the heat exchanger may still be worth it, even though we weren't able to achieve the 1 megawatt of heat load output. Depending on the cost of the refrigeration cycle, it could still be cost efficient to build the heat exchanger and take some of the load off the high cost refrigeration unit. Further financial analysis would need to be done on the current refrigeration unit in order to determine the return on investment time period. In order to build our heat exchanger, we enlisted Enquip Group, a company in Wisconsin. Their close location we thought would make it easy for shipping, as well as they specialize only in heat exchangers, so that we thought that they would be an excellent candidate for building our heat exchanger to the design specifications. Thank you.